In this video, we're going to take a look at the 5 main types of reactions and also consider how we can predict what the products of the reactions will be. You've studied reactions being classified into these 5 categories before in grade 10. The difference is we will look at them in a little more detail in grade 11 and also work on predicting products. The first category we'll look at is combination or synthesis reactions. Some of your teachers in the past may have called them addition reactions. In a combination reaction, we have 2 small things reacting to make one big thing. So when you look at what you have before the arrow and what you have after the arrow, you'll notice that on the reactant side there are multiple small pieces, and on the product side there is typically only one synthetic piece. What we see has happened is that these 2 different substances have somehow fused together to become one. When we consider how to predict the products, there are actually 5 big categories that we can use. I'll do an example for each. Let's consider a binary oxide reacting with carbon dioxide. Binary means 2, and oxide means one of the 2 things has to be oxygen. So let's try sodium oxide. We know sodium gets a +1 charge and oxygen a -2. So the formula for sodium oxide is Na2O. If it reacts with carbon dioxide, it will produce a carbonate. A carbonate is a CO3 group that has a -2 charge. This accounts for the carbons and the oxygens. The missing element we're going to need is the sodium. So the reactant or the product that's going to form will be sodium carbonate. I need 2 sodiums with a +1 charge to cancel the -2 on the carbonate. This would work for any binary oxide. For example, we could have also tried iron 3 oxide. If it reacts with carbon dioxide, it would also form a carbonate. The carbonate accounts for the carbons and the oxygens. We also will need the iron 3. So we will produce iron 3 carbonate. Doing the crisscross, we come to the formula, Fe2 brackets, CO3 taken 3 times. These equations that I am writing are unbalanced. We can balance them later. Never try to balance an equation while you're figuring out the crisscrosses for the products and the reactants. In the next example, we talk about what happens when a binary salt reacts with oxygen. Now, to a chemist, a salt is just an ionic compound, but specific to this one, it's going to be a metal plus a halogen. I'm telling us it's going to form a chlorate, so the halogen I'm going to choose is chlorine. However, if I chose the halogen bromine, it would form a bromate. If I chose iodine, it would form an iodate. So chlorates get a charge of -1. Let's pick the most common salt, sodium chloride. If it reacts with oxygen, remember oxygen is diatomic, it will form sodium with chlorate. Chlorate accounts for the chlorines and the oxygens because sodium has a charge of +1 and chlorate has a charge of -1. The formula that we get is NaClO3. This would work for any binary salt with oxygen. It doesn't have to be sodium chloride. I'll do another example. In this case, the binary salt that I'm choosing is magnesium bromide. It's still binary because there's only 2 different elements. Because I'm using bromide, instead of forming a chlorate, I'm going to form a bromate. Bromates are still groupings with a -1 charge. We discussed the formation of various polyatomic ions in a previous lesson. When magnesium bromide reacts with oxygen, it will form magnesium bromate. Magnesium gets a +2 charge. Since bromate has a -1 charge, I will need 2 of the bromate groups to cancel the +2 charge on the magnesium. The most simple version of synthesis reactions are 2 elements react to make a compound. Any 2 elements react to make a compound. If I chose sodium and chlorine, these are both elements. When you write the formula for an element, you need to ask yourself, is it diatomic? Sodium is not diatomic, so I can write it simply as Na. Chlorine, however, is diatomic. There are 7 elements on the periodic table that are called diatomic. They always come in groups of 2. They are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. You can remember them from the phrase, I have no bright or clever friends, or the more tongue-in-cheek phrase, I have no fear of ice-cold beer. Whatever helps you to remember, these 7 elements in their pure form come with a small number 2 beside them. When they react, they're going to form a binary compound. In order to figure out the binary compound, first think about the ions available to you. Sodium, I know, gets a charge of +1. Chlorine, -1. So the formula, when I do a crisscross, is NaCl. At this point, we can balance the equation with coefficients. What about a non-metal oxide in water? Non-metal oxides means that we're going to take a non-metal, any one you want, and react it with water. Suppose we pick the non-metal carbon. A non-metal oxide with what could be carbon dioxide. Carbon dioxide is the gas that you exhale when you breathe out and is also a major contributor to greenhouse gases. If it reacts with water, it will produce an acid. An acid is hydrogen plus a corresponding anion. So let's think this through. We know hydrogen has a +1. I now need an anion that accounts for the remainder of the elements. We've got carbons and oxygens. A quick check of common polyatomic anions tells us that carbonate is a common polyatomic anion. Carbonate gets a charge of -2. When I do a crisscross, I form hydrogen carbonate, also called carbonic acid. This is why greenhouse gases are contributing to the acidification of our oceans. As the carbon dioxide in our atmosphere increases, it combines with the water in our oceans to form carbonic acid. What happens if we have a metal oxide? A metal oxide could be as simple as any metal that you could imagine. Let's take potassium. Potassium has a charge of +1, and oxygen a charge of -2. A non-metal oxide might be K2O. If it combines with water, it will form a base. Bases are some cation plus a OH group. So I need a cation plus the grouping OH, which I know has a -1. The cation that we will use is potassium. Potassium has a charge of +1. So we're going to get the form KOH, which is potassium hydroxide. The next category of common reactions are decomposition reactions. I always recognize a decomposition reaction when I look at my reaction and I see one thing and then an arrow. If there is only one species followed by an arrow, all it can do is decompose, break apart. It's going to break apart into 2 smaller pieces. These reactions are always the exact opposite of the synthesis reaction. So this binary carbonate broke down to give me the binary oxide and carbon dioxide. Writing any of our addition or synthesis reactions in reverse gives us a decomposition reaction. The next category I want to talk about are our replacements. First, a single replacement reaction. Imagine in your mind there's a couple dancing and somebody cuts in. In the traditional sense of the word, in formal situations, we always replace the one most like yourself. I use this analogy to help us understand how the replacements might happen. We need a single and a double. So in this case, we have chlorine wanting to replace somebody in sodium bromide. Chlorine is my element, even with the number 2 because it's a diatomic element. It's still an element. Sodium bromide is a compound. If you see an element and a compound, you have a single replacement reaction. Chlorine will replace the species most like itself. To figure this out, consider the ions that are available. So in your mind, think about what can be formed. Chlorine can make -1 ions. We have sodiums, they make +1 ions. and bromines can make -1 ions. What other positive and negative combinations can we form? Well, we've already tried combining the sodium with the bromine. Let's instead try combining the sodium with the chlorine. This would make NaCl. Always write the positive first in a compound. What would be off on its own, species replaced, would be the bromine. Anytime you write an element by yourself, you need to ask yourself, is it diatomic? And if it is, it gets a little 2. If not, you can write it as self. It's at this point that you're able to balance the equation. Not all single replacement reactions will go. To find out whether they'll go, you actually need to check a reactivity series. Atoms can only replace another atom if they are more reactive. So we technically should be checking to see if these reactions will go by checking a reactivity series. This is not going to be the focus of our attention right now. I am just interested in you predicting what the products will be, not in deciding at this point if the reaction will actually go as written. The other type of replacement reaction is the double replacement reaction. In a double replacement reaction, we have 2 compounds and an arrow. When I look at the reaction, I see a compound, sodium hydroxide. I know it's a compound because it has 2 names. Hydrogen sulfate. I know it's a compound because it has 2 names. This has 2 names, it's a double. This has 2 names, it's a double. Folks, we've got ourselves a double-double. Unless you're Canadian, you're probably not going to catch that joke. Double replacement reactions happen anytime we see one compound and another compound. Again, consider the ions available. From the name sodium hydroxide, we know that we can get sodiums, which we know to have a charge of +1, and hydroxides, which we know to have a charge of -1. From the name hydrogen sulfate, I know we can get hydrogens, which get a charge of +1, and sulfates, which get a charge of -2. What other positive-negative combinations can we form? Always stopping to consider the ions available to you and then wondering how else they can combine is a great way to predict your products. I've got sodium combining with hydroxide. This time I'm going to try combining the positive hydrogen with the hydroxide. This would form HOH, also called water. Although a little balancing trick, writing water as HOH instead of 2 H's and an O in the form of H2O is often an easier way to balance an equation, and both are considered correct. The other combination that we can make is sodium with sulfate. When we do a crisscross there, we get Na2SO4. It takes 2 sodiums to balance the -2 charge on the sulfate. Again, always write the positive ions first in a compound. Our final category will be combustion reactions. Specific to combustion reactions are reactions that contain carbon, hydrogen, and oxygen only. You must have all 3 elements present. A combustion reaction occurs anytime a compound containing carbon and hydrogen, and sometimes oxygen, burns. And to burn means to react with oxygen. These reactions always produce the same products, carbon dioxide and water. So when you see a reaction that has carbon, hydrogen, and oxygen only, it is incredibly easy for you to predict the final products because they'll always react to form carbon dioxide and water. So here includes a summary of the basic everyday words that I've used to help us identify the 5 main types of reactions. You're going to need to practice taking a look at what you see before an arrow and what you see after to first identify the type of the reaction. You'll also need to practice what could be formed as products. To think about what might be formed, consider what ions are available and how else can they combine. In your textbook, there are more explanation and examples to be found on pages 289 to 298. There are also several worksheets available in your work package where you can practice identifying reactions, predicting reactions, and there is still more practice available on balancing reactions.